Good morning. My name is Victor Calderon. I'm currently a fifth-year grad student at Vanderbilt University, and I'm working with Andreas Berlind. Today, I'll be talking about a predictor of cluster and group masses using machine learning. The outline of the talk is first I want to explain what group catalogs are and why we need them. Next, I'll talk a little about more of the traditional methods of estimating group masses. Then some of the methods, introducing how we train and predict group masses, and also some extra about predicting group masses using a different set of HUDs or velocity bias variables. And at the very end, my conclusions. Okay, the first thing is what are group galaxy catalogs and why do we need them? Group galaxy catalogs are catalogs that tell you which galaxy goes in which group. So for example, you have a group finder, let's say a friends of friends, you run it on a galaxy catalog, and then the algorithm is going to put galaxies into group based on some distance from galaxy to galaxy. So group galaxy catalogs are interesting and useful because they let you study the properties of galaxies as function of other group properties. For example, you can look at the color of galaxies within a group, or you can also look at the environment. Uh, um, at the environment. You can also probe how dark matter halos trace large-scale structure of the universe. In the past, multiple catalogs have been used by multiple surveys, including SDSS, Las Campanas Redshift surveys, Deep2, among other ones. So they're really practical in the sense that they try to give you an insight into how galaxies behave within a group environment. With a catalog, you can also estimate a set of different statistics. For example, you can look at the group multiplicity function or look at the environment, the size, velocity dispersion of groups. You can also distinguish between centrals and satellite galaxies, and among other things. With that all said, one of the main parameters that define a galaxy group is its mass. Mass is important because we believe it can affect many different properties, like galaxy properties, like color or specific star formation rate and everything. So it's important to actually get a good estimate of the mass using some method. In the past, a lot of people have tried to estimate the group mass using dynamical estimates or abundance matching. So the main two traditional methods that people have used are halo abundance matching and dynamical mass estimates. The first one, it connects observation to theory, meaning you abundance match a theoretical quantity to an observed quantity. In our case, we say that brighter systems get assigned larger masses. On the other hand, dynamical mass estimates, they use the velocity dispersion or the kinematics of galaxies within the group to assign a halo mass or a group mass. In this case, more massive groups tend to move faster. In here, I'm showing a plot on the x-axis. I have the predicted mass using one or the other methods, and on the y-axis I have the true halo mass of galaxies. This is taken from a simulation, and each point depicts a galaxy. As you can see, this is not a perfect method. These two are not perfect methods, meaning they tend to overestimate or underestimate the actual mass. So you can see on the upper left is where halo splitting happens, and on the lower right is where halo merging happens. So we would like to improve on these estimates. Another way to look at it is if you look at the fractional difference between the predicted mass and the halo mass. this is um, more interesting because it tells you that dynamical masses tend to underestimate the actual group mass, while they both tend to overestimate by a factor of 10% in log m at higher masses. Now these estimates, they include errors in the masses, and they also include systematics like halo merging and halo splitting if you're using a friends of friends algorithm, for example. The aim of the project is we want better group mass estimates so that we can construct more accurate group galaxy catalogs and therefore have better masses. So the goal of the project is to use machine learning to create a machine learning based predictor of group masses using features from group and galaxy related observables. We also want to determine which properties are the best ones to use when predicting group masses. So the first thing that we do is we have a set of 100 mock group galaxy catalogs from Last Llama simulation. Last Llama simulation is a suite of simulations that fit the clustering of SDSS for a given luminosity for a given volume limit sample. We use a best fit values for HOD that match observations in SDSS, specifically SDSS 07 for the minus 19 R1 absolute magnitude volume limited sample. We also perform group finding using the Berlin 2006 Friends of Friends group finder. And later we compute galaxy and group related properties. These properties are the ones shown here. For example, it includes the shape of the group, its velocity dispersion, the luminosity ratio between the first and second brightest, group richness, total brightness, etc. And in terms of the galaxy related properties, you use the luminosity of the galaxy, the specific star formation rate, color, morphology, the galaxy type that you assign based on its R-band absolute magnitude, and also how far it is from the group center. So we use all of these features, as you can see here, and here I'm showing you the correlation matrix, and you can see that there are some are correlated, some are anti-correlated. But from these, the idea is we want to take a subsample of these and train the algorithm to predict halo masses. What we do in order to determine which features we want to use, we actually train all algorithms on all of these properties and select the ones that contribute the most to the predictions. And for the sake of time, I'm not showing results for that part, but what I'm showing is the different machine learning algorithms that we use, and also the results for that we get using that subset of features. So for this, we use a set of 3 machine learning algorithms: XGBoost, random forest, and neural network. XGBoost is similar to a gradient descent algorithm. Random forest is a compilation of decision trees, and neural network is a set of hidden layers with that try to determine the mapping of the different features. And the last step is we make predictions of group masses using this trained machine learning algorithms. In order to once we've trained the algorithm on all of these features, we want to validate and also see how well the algorithms are performing. So the first thing that you can do is you can plot on the x-axis the predicted mass that you get from the algorithm, and on the y-axis the true mass, each point being a galaxy. And the last 2 plots on the right, they show you the 2 traditional methods. So with this plot, it's a little bit difficult to see which one is doing better. So one thing that you can do is look at the fractional difference as a function of predicted mass. In this case, predicted mass is similar to what an observer would see. So if we look at the fractional difference as a function of predicted mass, we can see that across the board, the machine learning algorithms are outperforming the traditional methods as a function of mass, as a function of predicted mass, meaning that they don't overpredict or underpredict as much as the other two methods. So in this case, the predictor is actually getting more accurate masses than traditional methods, and they're all comparable to each other. Another way to look at it is instead of looking at it as a function of predicted mass, you want to know by how much your predicted mass is off from the true mass. Meaning, if you take the absolute difference between the predicted and the true mass that you get, and compute what that difference is for the top 68% of the galaxies, then you can see by how many decks your mass estimate is from the truth. In this case, they average to about 0.3 decks from the truth, while for Halo abundance matching it's about 0.42, and dynamical masses is about 1.15. Meaning, if you estimate a Halo abundance match mass of 10 to 11, then your true mass can be anywhere between 10.6 to 11.4. So in this case, this is showing that the machine learning algorithms are actually outperforming as well the Halo abundance match the Ham and dynamical mass estimates. The 1 sigma error in log M is much lower than those of traditional methods, and therefore these three methods are more accurate than the traditional methods. Another thing that you can do is you can look at which features are the more important ones when determining group masses. So here I'm showing you on the x-axis is the importance ranking. The shorter the bar, the smaller the bar, the more important the feature is. So to the left it's more important, to the right it's less important, and on the y-axis I have the different galaxy properties that we use to train the algorithms. I'm showing you the results for the two different machine learning algorithms, because for neural network you cannot compute this statistic. So from this we see that the galaxy luminosity at the projected group size and the galaxy color and velocity dispersion, they are among the most important features that we use. So this is to say that if you want to get a better estimate of group masses, these are the features that you would focus on. As an extra, we also want to know how different this would be if we have a different set of HODs, meaning we train the algorithm on one HOD model and try to test it or predict the masses from a different HOD model. So what we do is we have 8 different HOD models, and we train it on the fiducial model with no velocity bias and a fixed set of HOD parameters, and then we predict it using we predict it from different sets of HODs. So on the x-axis you have the predicted mass that you get from the algorithm or the traditional methods, and on the y-axis you have the fractional difference. This is also saying, so this plot is saying that at lower masses they actually don't do as well as the traditional methods, but on the higher masses they actually are doing much better. So the left and right plot is for XGBoost and random forest algorithms, and as you can see they mostly behave similarly, but they still outperform the traditional methods. Another thing that you can do is that you have a fixed HOD, so you don't change the HOD parameters, but you modify the velocity bias, meaning the velocity bias tells you how different the velocity bias from matter and dark matter. So what we do is we also have a fiducial model which has no velocity bias, and then we train the algorithm using that model. And then we test it on various different models that range from 90% velocity bias to 110% velocity bias. And from this, you see that there is actually not much of a difference between what you get from the different models. They also outperform the traditional methods, and surprisingly, the difference of velocity bias doesn't really matter as much. So to conclude, we investigated how traditional methods can under and over predict group masses. They actually do it by a factor of 2 to 3. We train a machine learning algorithm on different features related to the galaxy and group properties, and we actually get better mass estimates within 0.3x from the true halo mass. We also determined that the galaxy's luminosity, color, the group velocity dispersion are among the most important features for predicting group masses. And we also determined that we can use this estimator to predict masses from models that have different HOD parameters or have different velocity bias values. With that said, thank you very much, and I'm open to questions. Thank you.